Hello, class. Today we're going to talk about heat of reactions, and what I wanted to do is I wanted to work a class example. What we're going to do is, it's not quite a heat of reaction, but it's very close. What it's going to be is a heat of solution. And you got to see this when we mixed sodium hydroxide in with water. You may have noticed that the temperature of your solution went up quite a bit just by mixing the sodium hydroxide, the NaOH, into the water. Now, we'll need a couple of things. What we're going to do is we're going to work a problem where we mix a 10% solution of sodium hydroxide. And we'll have a couple of assumptions. One of our assumptions is that everything is going to start at 70 degrees Fahrenheit. And we're going to make a 10% solution. And what we'll do is, it doesn't really matter how much we make, but what we'll do just to give us some place to start with the math is we'll mix 10 grams of NaOH plus 90 grams of H2O. And so that'll be very similar to what you did in your lab. And the question that we have is, how hot is the resulting solution from preparing that mixture? One of the numbers that we're going to need is the heat of solution. And that number is pretty easy to get. I just looked it up on the internet. Wikipedia had a number for me, and it was negative 44.5 kilojoules per mole. And you'll remember the joule is a measure of energy, much like a BTU, and we have a conversion for that. And we'll pull that out when we need it. We don't need it quite yet. And then we can figure out how many moles we have of sodium hydroxide because we have the mass. And we know the molecular weight of sodium hydroxide is 40.0 grams per mole. And so that's a handy number. You know how to calculate that. We've used it enough times where we already know what the molecular weight of sodium hydroxide is. So let's go ahead and get started on our calculation. I guess one of the first things we'll want to know is how much energy is released. And to do that, we can start with our standard method, which is to write down what we know, and then use conventional unit conversions to get us into a number that we can do something with. And so in this particular calculation, a good place to start would be how much sodium hydroxide we have. And recall, we have 10 grams of it. So I'm just going to write that down. 10 grams of I'm going to write a little bit smaller now, NaOH. And then we'll want to decide what we need to do with that. And we can convert that into moles easy enough because we have the molecular weight. And so why don't we write that down? And this is going to be a divide, which is 40 on the bottom grams per mole. And then the grams are going to cancel. And then looking up above, I see that I have the heat of solution in kilojoules per mole. And that looks like that's going to be a multiplying. Now, the negative is an important thing to keep in mind. And you'll recall from our discussion on heats of reaction, what that means is that it gives off energy when we make the mixture. If it was positive, it would consume energy and it would get cooler. We don't need to worry too much about the sign right now because we know it's going to get warmer. And so I'm not going to worry about the sign. I'm just going to write down the number, 44.5 kilojoules per mole. And when we work that out, we're going to get 10 divided by 40 is a quarter. And then 44.5, I probably should have got me a calculator, but we can cut that into a quarter pretty easy. So it's going to be 11.1. pretty close to that, 11.1 kilojoules. Okay, so now we know the amount of energy released, 11.1 kilojoules, for mixing 10 grams of sodium hydroxide with 90 grams of water. Let's go ahead and convert our kilojoules into BTUs, which is a number that we're more familiar with using. And I have the conversion here, and we'll just write it out. And that's 1 BTU is 1.06 kilojoules. And so the 1.06 is going to go on to the bottom. So my units cancel, is equal to 1 BTU. And then that's going to keep us pretty close when I type that into my calculator. 11.1 divided by 1.06. It doesn't change very much. I come back with 10.47. We'll just call it 10.5, which is close enough for what we're doing. So 10.5 BTUs. Make sure that looks like a 10. And so we're in pretty good shape now. And we know what a BTU is, right? 1 BTU is equal to 1 pound of water, 1 degree Fahrenheit. Now, we don't know how many pounds of water we have right now, right? Because that wasn't in our problem. But we do know that we were going to start our solution with 90 grams of H2O. And so I'm going to add that in there. And then we're going to mix in 10 grams of sodium hydroxide. So when we're done, we have 100 grams of solution. Now the heat capacity of that solution isn't exactly water, but why don't we start out with that assumption, and maybe we'll come back and fix it up a little bit later. And so what we have is we have 100 grams of solution, and we can turn that into pounds. And so we can use our favorite conversion, which is 454 grams per pound. And when we come out with that, we're going to get a little less than a quarter pound. So 100 divided by 454, we get 0.22 pounds. 0.22 pounds. And then let's go ahead and use our definition of BTUs. I'm going to put 10.5 BTUs, and then I know that 1 BTU is equal to 1 pound of water, 1 degree Fahrenheit. My BTUs cancel. And then what I need to do is I need to put the pounds on the bottom here to make pounds cancel, 0.22 pounds. And then when I calculate that out on my calculator, let me scroll down a little bit for you. We're going to, okay, where I was at, I had to restart here. I ran out of time on my recording. And so where we were at is we had just finished this calculation to figure out how much heat we were going to have for a heat increase, and our answer was 47.7, and I was just writing that down. So let's continue there, 47.7, and the units for this are degrees Fahrenheit, because that's what's left in our equation. Now, that's the temperature rise. We started at 70 degrees, and so add 70 degrees Fahrenheit where we started, and what that's going to give us is let's take a look at that. That's going to give us 100 and, am I doing that right? 117 degrees Fahrenheit, if I did that right. let me think. So 7, that's right, 117 degrees Fahrenheit. And so a pretty big temperature rise. Now, we've simplified this just a hair, and our simplification is that we assume the heat capacity of our solution is the same as water. In reality, the heat capacity of this solution is only about 90% of water. And what that means is that for 1 BTU and 1 pound of the solution, it doesn't heat up 1 degree. It'll actually heat up more than that. And so you'd have to take 1 divided by 0.9, which is just a hair more than that. So 1 divided by 0.9 is going to be 1.11 degrees Fahrenheit. Or to write it another way is that our heat capacity would equal 0.9 BTUs per pound degrees Fahrenheit. And you just have to be careful to make sure that when you do that, you take whatever you find on the internet and you make sure that it comes out the right way. And this is the right way, because what it says is that I only need 0.9 BTU to heat up 1 pound of water 1 degree Fahrenheit, i.e. it would heat up more than water would. And if we did the math again with this, what we could do, and I won't worry about I'll write this a little bit smaller here. What we'd have is 10.5 BTUs times our heat capacity, and again it's going to go on the bottom, is 0.9 BTU per pound degrees Fahrenheit, and then we had 0.22 pound, and we'll cancel our units, and again we come up with degrees Fahrenheit, and when we type that out, 10.5 divided by 0.9 divided by 0.22, and we get 53 degrees Fahrenheit for an increase. And then of course we'd add in, and I'm running out of a little bit of space here, so let me slide over to the side. We'll add that to our 70 degree starting temperature, and that's going to bring us up to 123 degrees Fahrenheit. And that was only making a 10% solution of sodium hydroxide. Now, one of the things that I'll put in the slide, the video when I'm done, is I'll put in a graph that I found from a manufacturer of sodium hydroxide, because this gives off enough heat that you need to manage it. You could imagine if we were making a 20% sodium hydroxide solution, our temperature rise wouldn't be 53 degrees, but it would be roughly twice that. And so 100 degree temperature rise. If you started with 100 degree water, you're going to be right near the boiling point of water. And you could have a container that just kind of bursts into boiling caustic. And of course that caustic is very dangerous for your skin, even more dangerous for your eyes. And so it's a hazardous material and it needs to be managed. And so we need to understand how this stuff is going to behave when we work with it. And so they've made a table that shows you how much heat's going to be released at different concentrations. And you'll see that it actually tells you with your starting temperature of your water what your final temperature is going to be at different concentrations. And as you can see from this chart, if we start with 70 degree water and follow that up, the chart shows us that our final temperature is going to be 120 degrees Fahrenheit or so, looking at the chart, which is an excellent agreement with what we came up with our calculations. And so that's all I have for this discussion. I hope it was useful. It should benefit you on your homework, and then we can talk more about it in class if there are still questions. Thank you.